Hey guys, in this video we are going to learn about probably one of the most important aspects of organic chemistry, which is chirality. So chirality is a property that an awful lot of organic molecules have, and it's really important to be able to identify when molecules are chiral. So because I'm terrible at art, I printed out some pictures to help me explain what I mean. So your hands are the easiest chiral objects to try and understand. So if you have your left hand and your right hand, they're mirror images of each other, okay? But what happens is that they can't be superimposed. And an example that you can use to try and understand this is that if you have a glove that fits your left hand, your right hand won't fit in that glove normally. So an easier way to understand it is if you take, say, this glass bottle and you draw the mirror image of that bottle, they can fit on top of each other. They can be superimposed really easily. And an easy way to identify that is if you can draw a line down the middle, like so. You can imagine folding along that line and it'll be perfectly in half. You can't do that with your hand, because if you were to try and fold it down the middle, it doesn't work because you have a thumb sticking out here and you don't have one out there. So they're not symmetrical. Chiral molecules are not symmetrical. So this becomes really important in biology, and probably one really cool example of this is in glucose. So basically all sugars come in two chiral forms. So you have, when it comes to sugar, they're denoted as the D hand of glucose and the L hand. Okay, so the way you draw the enantiomer is if you were to draw a mirror plane down the middle and you imagine you draw the reflection on the other side of it. So what I usually do is, to make it a bit easier, is I'll draw the circle, the 6-member ring first, and then I will just copy each one across. So if this is on the right, now it's going to be on the left, and you do that all the way around. And so if this is on the right here, it's going to be on the left in its mirror image. And you just draw that all the way around. And for particularly big molecules like this, sometimes it can be hard to see that they're not superimposable. But as you can see, so at the moment, if I were to cut this out and try and put it on top of this molecule, they're not going to overlap properly. The only way to make this overlap would be if you flipped it over. But what would happen then is if you take this group here, so what this wedge means, so if you see a bond that looks like a filled in triangle, what that means is you're trying to show that this OH group is actually sticking up out of the page towards the camera. And if you see a dashed bond, so it's a triangle that's made up of a few lines, what that is implying is that the OH group is actually going behind the piece of paper. So if you were to flip this molecule over so it has the same orientation as this one, what would happen is this OH is currently sticking up, but if you rotate it 180 degrees, it's going to be sticking down. So that's why these are not superimposable. So to try and make that a little bit more clear, if you take these two molecules here, okay, so I'll put them on the correct side. So if you look at them here, this is the left hand of an amino acid, and this is the right hand of an amino acid. And what you can see is that these are mirror images of each other. So if you imagine there was a mirror down the middle here, they're mirror images of each other, much like in this picture of the hands here. But what you'll notice is that in this case, the OR group is sticking up towards you and the hydrogen is on the left. So the hydrogen is kind of like the thumb. But when you look at the mirror image, the hydrogen is over on the right now, and that means they're not superimposable, because if you try to overlap them like this, okay, it's kind of hard to see, you can see that the hydrogen is on the right in this case and on the left on that case. So there's a few tips for being able to identify chiral molecules. One of the biggest indicators, and it's not always present, if you see a dash bond or a wedge bond like this, that's a really easy way to identify that there's a chiral center. Another one is what I said here. If you can't fold the molecule in half, there's probably a good chance that it's chiral. So a really famous example of this is thalidomide, and it was a very sad example as well, and I'm sure most people have heard of it. So thalidomide is this structure here, and it comes in two enantiomers. So this bond in the middle, okay, that indicates that the molecule is chiral. So this carbon here is chiral. And I'll go through a little bit more details about how you identify chiral carbons. So one of these enantiomers very successfully treats morning sickness, and it's very good at doing that. The other enantiomer causes deformities in the unborn child. And unfortunately, even if you make one enantiomer, the body will actually turn it into a mixture of both enantiomers. And that's why thalidomide is no longer used for treating morning sickness. So how do you identify a chiral center? So as I said, if you see a dash or a wedge, that's usually a good indication, but it doesn't confirm it, okay? So a chiral carbon is a carbon that has 4 different groups attached to it. Okay, so if A, B, X, and Y are all different, that means this carbon is chiral. So a really common example of that is an amino acid. So this is the structure of a typical amino acid. Okay. So if you look at this carbon in the middle, okay, all 4 groups attached to that carbon are different. This one is a carboxylic acid, this one is an amine, this one is a methyl group, and this one is a hydrogen. So all 4 groups attached to the carbon are different from each other. So what that means is if I were to redraw it like this, okay, so instead of the amine group sticking up towards the camera, it's actually sticking down through the page. These are enantiomers of each other, okay? So in the next video, I'm going to be giving you a good few more tips on how to draw an enantiomer, and also how do you assign the stereochemistry. So while in the terms of sugars, they're often called L, D, and L sugars, what's more commonly used is a system that involves calling them S and or sugars. So there'll be a lot more detail about that. And that's a very, very common question in university exams is what is the configuration of a chiral center? So in the next video, I'll go into that in great detail. Just remember that all these videos are part of a fundraising thing that I'm trying to do to raise money for Cystic Fibrosis Ireland. The link to the GoFundMe page is in the description below. So if you'd like to see more videos like this, please do donate if you can. Thanks.